Good morning and welcome to the Vic South livestream Star Party, presented to you by the Astronomical Society of Victoria and the Astronomical Society of South Australia. Before we begin today's stream, I'd like to say that in the spirit of reconciliation, the Astronomical Society of Victoria acknowledges the traditional custodians of country throughout Australia and their connections to the land, sea and community, and we pay our respects to their elders past and present and extend that respect to all Aboriginal and Torres Strait Islander people today. This morning, we're bringing you astrophotography session, Hunting for Exoplanets, presented by the ASV Astrophotography Section Director, Tom Fowler. Tom will show us how to hunt for exoplanets in light polluted skies. Before we begin, though, I'd like to remind viewers that we still have our raffle running. It will be drawn this evening at around 9 p.m, so you've still got a chance to grab a ticket. Links on the ASV Facebook, the ASSA Facebook, the ASV website. First prize is a Skywatcher Star Adventurer mini kit valued at $699, and second prize is a 40-inch long telescope carry bag valued at $299. Big thank you to our sponsors, TSA Outdoors, for sponsoring the Vic South Star Party. And as always, if you're enjoying today's stream, you can donate stars on Facebook and stickers on YouTube. And we always appreciate all the donations we do get. If you're watching us for the first time, don't forget to subscribe to both the ASV's and the ASSA's YouTube pages and follow our Facebook pages. But for now, we'll bring Tom in and get the discussion started. Good morning, Tom.
G'day, Mark. How are you?
Good. Yourself?
Very well, thank you. G'day to all our fellow astronomers and astro imagers.
So if you want to share your screen and start your presentation on hunting for exoplanets.
I need to share my screen, which is a good place to start. More difficult than I would expect. Give me a hint here, Mark.
You got it? So there's a button down the bottom that says share.
Not yet, just a moment. I'm resizing a window here. Share.
This is technology working at its finest at the moment.
There we go.
There we go. We've got it. We're up and running.
We're running?
Yep. All yours.
All right. Well, it's been a difficult couple of years with COVID and whatnot. But I've really found astro imaging, astrophotography to be my rock. It's been I think it's been the source of my sanity during these past couple of years. Although it's certainly been heavily impacted. Travel restrictions have kept a lot of people away from their normal dark sky sites and forced people to image in their cities in cases where they've been under restrictions. And that severely limits your opportunities. Now, I'm not claiming that this is my position. I've not been anywhere near as impacted as that with a remote observatory, but many people have been, and I feel for them and their frustration. Narrowband imaging's been an opportunity to deal with light pollution and other things, but I find it a bit limiting. As I say, I do operate a remote observatory designed for taking pretty pictures. I have got a slideshow here of pretty pictures if you are interested, but I don't know that we've all seen pretty pictures. Yeah, so we'll skip that. I operated a 250 millimeter f5.8 CDK made by Stefan Buddha with a QSI CCD camera with LRGB and HA filters, unless I can get to the observatory to put the narrowband filter wheel in. So there's my weak point as far as COVID's concerned, is I don't have the opportunity to change to narrowband filters. And after imaging like this for a number of years, I've realized that I'm actually taking far more HA than I ever put into my final images. If the moon's up, I've been imaging HA exclusively, and there's about half the imaging time every month has the moon present. So I've captured a lot of HA and not been able to make the most of it in terms of publishing images from it. So I've been looking for an alternative to shooting HA, and Chris Roach, the president of the ASV, popped an earwig in my ear, put an idea in my head, to see whether it was feasible to capture an exoplanet transit. And that sent me down the rabbit hole. So to begin with, I wondered how many exoplanets there were and whether they were accessible to us. I had a look in Stellarium, always a good place to start. And all of those purple dots are exoplanets that are in the sky of my observatory at 2100 hours tonight.
That's a lot of exoplanets.
There's no shortage of exoplanets. If I just hide the horizon and zoom around here a bit, you'll see that some parts of the sky have a lot of exoplanets. There's clearly been a large survey done in this part of the northern sky. But yeah, just exoplanets that are visible from Victoria or South Australia. There are no shortage of them at any time. But how many of these are transiting exoplanets? It's maybe a different story. And how many of them are transiting tonight? Certainly a different story. So I needed to find sources of exoplanet data. The British Astronomical Society has a project on exoplanets and have a lot of information. This is actually a how-to tutorial on exoplanet hunting. And their advice is almost any instrument. So from a DSLR, they say to a 400 millimeter CDK, but I think the sky's the limit. Any instrument you have can be used for confirming an exoplanet transit. Here's another interesting resource that details the transiting characteristics of 3,262 confirmed planets. This website will present you with a table showing when each of these will transit and how deeply it transits and for how long it transits. But it seems that it was a project, a guy's PhD project, and it doesn't seem to have been updated since 2018, which is fairly recent. But when you consider that we found the first exoplanet in 1985, it's the recent discoveries that are significant. So I was after something more contemporary, and I found a site here that has been very useful. We'll have a look at this in just a moment, but it lists exoplanets. It allows you to filter for planets that are visible from your location on a date and at a particular part of the sky, which are really handy if you want to try and image an exoplanet tonight. How do you find one that will actually transit? This site will show you, and it'll give you a finder image that is particularly handy when you capture an image that has 1,000 stars in it. Which one has got your exoplanet? And it's based on an archive from NASA of 3,302 planets when I looked today. And let's have a look at this site. This is the site. So you can select. We don't need a calculator for this. You can select the NASA database. You can choose your observatory location, and because of a peculiarity in the website, I use Mount Stromlo because it's in my time zone, but you can equally well enter a latitude and longitude and a time zone, but maybe they fixed that. It wasn't allowing me to enter a time zone when I went for a particular lat long. And so I was left with UTC only. By choosing Mount Stromlo, it's in my time zone. I get times in local time. You can choose a date, and for reasons that will become apparent, I'm just going to whiz this up now with the 10th of this month. You can choose a number of days to sample and before or after. And you can select a minimum altitude at the ingress and egress, at the beginning and or at the end of the transit. And I've chosen 40 degrees there because my observatory automation software is set up to limit with a limiting elevation of 40 degrees. So here we have a table of exoplanets that transited on the 10th of the 10th. And there are a few, 2, 4, 6, 8, 10, 12. There were 12 of them that night. Some of them weren't particularly deep transits. This one is a depth of 0.73 parts per thousand. Experience shows me that I don't have a chance with that one. I need a lot deeper transit than that. And in fact, this guy here, WASP 4b, with a depth of 23 parts per thousand was the best option on that night. This guy might have been interesting too, 31 parts per thousand. But I chose WASP 4b that started transiting at 22:39 local time, peak transit at 23:44 and egressed at 00:49 on the 11th. The recommendation is to image from an hour before the transit starts to an hour after the transit starts, to get an hour after the transit ends, to establish a baseline. Now, this other points of interest on this website are the visual magnitude of the star, pretty important. The times, the elevation at each of those milestones during the transit, a diagrammatic representation of the transit, yeah, fair enough, and the azimuth, yep, we can find it. We've got RA and DEC there too. Now, this is a finder chart for the star in question, and that'll come in handy later. So that's the website that I use to choose targets and to plan my observing campaign. The next question, once I've found a target, is how do I optimize my imaging session for this unusual role for the equipment, because it's not imaging for pretty pictures, and there are some differences. There are also a lot of similarities. So I say here, it's just like shooting pretty pictures. You can use a one-shot color camera, you can use a mono camera, lume filter in my case, or you can possibly use other filters. I found it handy to plate solve accurately to the target, because it's still a task to find your star in a field of 1,000. And then the aim is to take lots of subs from an hour before the transit starts until an hour after the transit starts. The transit ends. But there are also some significant differences, particularly for a bright star. It's common to use a diffusion filter, or to defocus your telescope and to limit the peak ADUs that you capture for this star. A 4-width half max of 10 arc seconds apparently is quite okay for this sort of work. I couldn't get to the observatory. I don't have a diffraction filter. So my magnitude limit was possibly affected by not being able to use a diffusion filter. You need to expose the star in question within the linear range of your sensor. I aimed for the same ADUs that my camera manufacturer recommended for shooting flats. And it turns out that this is about a 30-second exposure for magnitude 11 stars, or about a 10-minute exposure for magnitude 14.5 star. So you can see there's quite a range of exposures there. And it was an interesting process to get my head around and measure the correct exposure for a range of stars. And as you'll see later, I had more than just the capture of one exoplanet light curve in mind when I attacked this, and I was actually intent on introducing exoplanet transits as another type of object that I could add into the observatory schedule and capture remotely and automatically. It's better not to it's certainly essential to guide while you're imaging, but it's better not to dither. You actually want your exoplanet star and others on exactly the same part of the sensor throughout the night, throughout the imaging session, because you don't want variations in the sensor to impact the data. You want your exoplanet to fall within the same dust bunny throughout the night. So, or on the same dead column of the sensor. So turn dithering off. And when you've captured your series of light frames, you calibrate them as normal with, in my case, darks and biases and flats, but you don't stack them. You deal with calibrated light frames. So you have a folder with 150 30-second subs or 50 10-minute subs. How do you compute a light curve? There are several software packages available that'll do this. VFOT is an online tool offered by the American Association of Variable Star Observers. You need to be a member of the ASVO to use the tool, but it provides a photometry program analysis that will plot a light curve from a set of images. Apparently AstroImageJ will do it too, although I've not looked at that, because I use ASTAP as a plate solver. And it turns out that ASTAP is becoming the Swiss Army knife of astroimaging. It's a fabulous tool for plate solving, the best plate solver I've come across, fast and accurate. It will also calibrate and stack. And apparently it now does photometry. So I thought, this is the tool for me, let's give it a go. And now's the time to jump into the example. Here is ASTAP for those that haven't seen it. this happens to be an image of with an exoplanet in it. We'll get there in a moment, but it has a number of interesting functionality. It can do a plate solve of your image that just plate solved this image in 0.2 seconds. So blindingly fast plate solve. It can annotate stars. And in fact, what it's just done now is it's a photometric analysis, and it's displaying the magnitude of each of these stars. So this guy is a magnitude 14.7, for example, 16.7. Let's clean it up. And annotate unknown stars. These are stars that are not in a catalogue. So that's a magnitude hard to read, 10.5. Star that's not in any of its catalogues. Here's another magnitude 11 star that's not in the catalogue. If you have deep sky objects, it will annotate your deep sky objects. There are a few baby galaxies in this field. And so interesting to play around with. It'll annotate asteroids. You download the latest asteroid ephemera, and it will annotate asteroids on your field. But what I was interested in was in the stacking menu here. It allows you to load a set of light frames, and then to analyze them and do a photometric analysis. So if I just run through the process quickly, this is just analyzing the light frames, extracting the background in each of these frames, and doing an astrometric, ensuring that the frame is plate solved. So it knows where the plate is and where the frame is in the sky. And let me just let this run through. It's basically a three-pass process to extract a light curve. The first pass is this frame analysis and astrometric solution. The second pass is a preliminary photometric analysis where it estimates the magnitude of stars in the field. And the third pass is a refinement of that photometric analysis. So we're getting close to the end of this. How many subs are there in this data set?
So what's it doing right now, Tom?
It's plate solving each of those images. It's just finished now. How many are there? There are 118 images there. Okay. The next step is to run back through them again and estimate the magnitude of the stars in the frame. Now, just can stop it. It's done 3 frames, but let's have a look at this. This image is the finder image for my transiting exoplanet. You can see a circle here. That's the star with the exoplanet. Now, let me try and match the image scale. This bright star is here. A row of 3 stars heading up to 10 o'clock. And then a pair of stars with this guy being the variable star. So if I zoom in on that, its magnitude about 12.7. I now need 2 other stars that have about that same magnitude to compare, to ensure that as a reference, and to ensure that the reference isn't a variable star itself. So here's I see another 12.7 magnitude star. I'll use that as a reference star, and then I need a check star, and this guy is 12.8. I'll grab him. So I've selected 3 stars. Now we run through again, and it'll measure the magnitude of our stars, the variable star, and the check star and the 3rd star. And it'll run through once, performing a poor photometric analysis. And then in a second pass, it'll refine that analysis. So this is the time-consuming part of the process. It'll sit here and tootle through these 100-odd subs and take its sweet time. But maybe in the meantime, it might be worth having a thought about some other possible scientific projects that you could do that maybe aren't limited by the need for a dark sky. One of them that I happened across by chance is this is an asteroid I chanced across in my imaging of the Helix Nebula. You see this asteroid just moving across the field there. I used ASTAP to identify that it was 178 Mentha, and I just happened to notice that this was in the field one night while I was trying to capture some luminance luminance subs for that object.
It's pretty cool that you were able to detect that.
It's pretty amazing. I've been imaging from this observatory for 3 years, virtually every clear night, and it's the first time I've through happenstance bumped into an asteroid. I found a way of finding asteroids to image, but I haven't found a way of determining when there's an interesting conjunction. It's really the fact that the helix is in the background that makes this so much more of an interesting project, I think. But
it's a very cool little find.
It was happenstance. I haven't purposefully imaged another asteroid, but Telescopius gives you the ability to list the asteroids that are in your sky tonight, and so that would be that'd be another project that you could do from a light polluted sky. You might not find the conjunction that I stumbled across, but it's an interesting project nonetheless. I notice here that I'm going to have to start this again because it's gone off into the weeds, unfortunately.
What are you doing? What's happening at the moment in the background there on this? We're waiting for a process to complete, I assume.
We are, but we've not got the correct stars selected. I might have clicked on the image. There are our stars. I'm just going to run this through again. Get that out of the way. This is the star we found in the
image,
in the finder image. So that's the guy. That's WASP 4 in this case. That's the transiting exoplanet star. And I've chosen another magnitude 12.7 star as a comparison star. So if something happens, if there's a high cloud, for example, that would dim the transiting star. It would also dim the check star. And so the idea is that select two stars and look for variations in magnitude between those two stars. And just to make sure that is the check star itself isn't a variable star, put a third one in the mix. So I've selected three stars that are as close as I can get to the same magnitude, and none of them are variable. That's the aim. And the program's just going through and measuring the magnitude of each of those three stars. The first time through, it calls it a poor photometric analysis. Second time through, it's a more accurate result. So we need to actually let that cycle through the complete set of frames total of 3 times. We're 1.5 times through now. So yeah, this is the hold your patience in both hands section of the process.
Is this where we all go and make a cup of tea and come back?
It's where we make a cup of tea and come back, or
we answer a question.
We could answer a question, absolutely.
So, Yuri wants to know, please explain the meaning of part per thousand in the exoplanet list. Is that the depth? So in the exoplanet list, there was a part per thousand column?
There is a parts per thousand. It is the depth of the transit, or the reduction in the magnitude of the visual magnitude of the star. And it's parts per thousand because if you measured it in percent, it's not a very great, it's a small number. So these planets are not large, and they're orbiting fairly close to a bright star. And so they don't actually diminish the intensity, the magnitude of the star that much. So the measurement is done in parts per thousand rather than percent.
Wonderful. Hopefully that's answered your question, Yuri. It's a very good question.
Indeed it is. Where have I put my... just to... here we go. This is the field that Yuri's questioning, is 23 parts per thousand. 2.3% reduction in light during the transit. And some of these, some of the other data that's available here, the period in days of the transit. This is the length of the year for this exoplanet measured in Earth days. So this particular planet circles its star, its sun, every 1.3 Earth days. So it's very close to its star.
It's moving at a rate of knots then, isn't it?
And it's really whistling around. Some of them, here's a 0.79 Earth days.
0.28.
So some of them really whistle around. Some of them, the duration of the transit, particularly when they have a short period, this guy's transit is less than 1 hour. But he does it every, just over every 6 hours. He whizzes around. So this is a particularly close exoplanet. It must be very hot. And its transit is 0.41 parts per thousand, means that it's way outside the ability of my meager equipment to capture a transit that shallow. So just a quick look at how we're going here. Now, we're approaching the end of the second photometric swipe pass through the data. And you'll see that most of these now have a tick in the photometric column. We'll get to the end of the data set here and we'll be able to have a look at a light curve. So we're nearly there. 3, 2, 9 more. I'll stop that. And here we have...
Can we make that screen that you've got there bigger? That one with this graph on it?
I can do that. So in red, we have the magnitude of WASP-4b. Sorry, the magnitude of WASP-4. That's the star. WASP-4b is the planet. So we've got a magnitude scale here on the left-hand axis, the y-axis, and there's the magnitude of our star. In green here, we've got the magnitude of our check star. That doesn't seem to be varying. It's maybe it's reduced over here on the left a little bit. There might have been something related to the MS, for example. Yeah, we were shooting lower down later in the evening, so we're shooting through more atmosphere as we go on through this series of exposures. And so it's possibly accounting for the gradual reduction in the check star in green and the third star that we analysed here in blue. And we've got error bars on the magnitude measurement for the transiting star and the check star. And those error bars are related to the signal to noise ratio, primarily of the image that the data was extracted from. So that's a light curve from one transit of WASP 4b.
So what do you do with this data now?
Well, there are a few things that I found interesting about this data. You can estimate the mass of the planet and its distance from the star by the time it takes and the depth of the transit. The thing that I found really interesting was that on ingress here, this is the planet going onto the disk of the star. That slope is quite different from the egress slope. I think that's clearly a steeper slope on egress than it is on ingress. And this had me really stumped for a long time to work out why that might be the case. You look at the geometry and it's very hard to understand how they could be of a different slope. But, sorry?
I was just saying, we've got another question. Steve Wilkins. Yeah. Is a luminance filter best to use for identifying exoplanets?
It depends on the magnitude of your star, I expect. The tabulated magnitudes of stars are not normally measured through an HA filter. They're normally, I believe, they're measured through a green filter, a V filter, which happens to be similar to our green filter. But I mentioned the range of exposures that I have used. For magnitude 14.5 star, I needed a 10-minute exposure. And a lot of these exoplanet transits are of stars of the order of 14th magnitude. And so I was actually limited by the sensitivity of my instrument. And I chose the Luminance filter to be able to get down to mag 14 without exceeding a 10-minute exposure. And once I'd sorted that out, yes, I went for bright. I chose 14.5 magnitude as one limit of my range of magnitudes. The other end, I didn't want to go to less than a 30-second exposure because they become too noisy. The background extraction is too noisy. That was my reason for choosing Loom, but as some of these resources say, this website, for example, even talks about doing this with DSLRs. So one-shot color DSLR is not a problem. Doesn't need to be a Loom filter.
So now that you've got that data,
Yeah.
what do you do with it? What can be done with it other than trying to calculate mass and?
Like pretty pictures, you can collect this data, collect light curves. The next question that I came up with was, well, to actually understand some of the features of the light curve. I wanted to understand why it was this shape. And can I just slide these? If I slide that across like that. It turns out that they are traditionally U-shaped. They're always U-shaped light curves. And if they appear to be V-shaped, it's actually, V-shape's an indication of a variable star rather than a transiting exoplanet. And the reason for this is that the illumination of the star is not even across its face. This image of this artwork here shows the issue. The illumination at the edge of the star is not as bright, and so as the planet is obscuring the disk of the star, it's obscuring a less bright part of the star at the beginning and the end of the transit, and its peak brightness is in the center of the disk. So the characteristic of an exoplanet transit is a U-shaped transit rather than a V-shape. Now, this example could almost be V-shaped, but apparently U-shape is an indication of an exoplanet transit. And the trough here is also often associated with noisier readings. Now, this particular example doesn't indicate that, and I think you'd need to look at multiple transits of the same exoplanet to identify it. But if the star has star spots on its disk, the transiting exoplanet is crossing in front of sunspots and unaffected, or the star disk that is or isn't affected by sunspots. So the illumination of the background star varies. It can vary across the disk of the star, and that leads to a noisier light curve during the transit. And I mentioned the difference in slope here between ingress and egress. This is actually an indication of the eccentricity of the exoplanet's orbit around its star. If it's a circular orbit, ingress and egress will be a similar slope. But if it's an eccentric orbit, you can observe this different slope.
So also the gaps in that data there, is there a reason for those gaps being there?
There is. I run my observatory automatically, and it automatically refocuses every hour, and every second hour it changes target. And now in this case, it changed to the same target. But there's an introduction. There's a gap in the imaging while it slows to its new target, plate solves again, autofocuses again, and it actually this particular imaging session was interrupted by a lone cloud passing across the weather sensor. So the observatory actually shut down in the middle of this and then opened up and started imaging again. So it'd be nice to have a clear night with perfect seeing and no clouds, but we're not always that lucky. So the interruptions here are...
Not in Victoria anyway.
Sorry?
Not in Victoria anyway.
Yeah, certainly not in spring. So yeah, it's stuff happens and you don't always get all the data that you'd like in an image set. And just relying on a single transit, it's tricky. The other thing that can well interrupt your imaging is a meridian flip.
What was that?
A meridian flip.
Ah, yeah.
If the star crosses the meridian while you're imaging it, your system will, in my case, will flip the telescope from being on the west of the pier looking east. It'll flip over so the telescope's on the east looking to the star in the west. And that takes a little time to find the target again, replate solve and refocus. So there are a number of reasons an automated observatory will have gaps in its image sequence for this sort of work.
Now, you were talking before about using this data to calculate the mass and, I guess, the approximate location of the exoplanet. Have you done that yet?
No, I haven't done it. The other thing you can calculate based on that is what type of planet it is. Is it going to be a hot Jupiter? Is it going to be a super Earth? There are a number of categories of exoplanets, but all of them that are available to me with this instrument are probably hot Jupiters. I need an exoplanet with a really deep transit to be able to identify it with my gear, and they appear to be things with a very short year, repeat very often, and have this deep transit. And so I believe they're predominantly hot Jupiters.
Are you looking to try and do some of that work?
I am.
Yep. So the other question I've got then is for those viewers who are ASV members or even ASSA members. Is there a set of data, or are there sets of data that you've taken that they could get a hold of to learn this process as well? Is that something we could look at for them, perhaps?
I'm certainly happy to share some of this data. I'm still actively searching, trying to replicate transits of existing exoplanets, of known exoplanets. Yeah, and be very happy to share if anyone's interested in running the photometric analysis. I know the junior section is is looking at exoplanets, and I don't think it's a spoiler to say that they will be looking at calculating masses and the like in their next section meeting.
There you go. So if there's any juniors out there who want to, or any young astronomers out there who are keen to get involved in this, the ASV's junior section's working on this at the moment with the help of Tom, obviously, and Chris Rudge, the section director.
The juniors gave me a target to try and capture for them this month.
They picked one for you.
They picked one for me.
Did you get the data?
I've tried it on 3 nights now. And,
let me guess, it was cloudy?
I've had all sorts. I've had all sorts of fun and games. It's a particularly deep transit, and so I'm hoping for something that's more compelling than this light curve. And I've got to say, so far after 3 nights, I'm not impressed with the results that I'm getting, but I'll keep trying. It brings me to another point. What I have done is I've integrated exoplanet transit measurements into the automation of my remote observatory. So just as I can tell the observatory to image the Helix Nebula for the next month, well, that was last month, in fact, I can also point it at particular exoplanets, and it will image exoplanets from the NASA exoplanet database of 3,302 planets. Any one of those that's visible in my sky, I can slot into the schedule of the observatory and get what I can get. A more interesting and more difficult problem is the TESS objects of interest database. There are, at the moment, 4,547 objects of interest that TESS satellite has determined may be stars with exoplanets. But many of these are not confirmed as transiting. And so there are often no transit details, no period, no duration, no depth, and no next date and time of transit. Now, this is a very different problem, a lot more challenging problem. But nonetheless, it's something that I'm working on to tackle some of the targets on this database when the moon's up, because frankly, I'm shooting more HA than I can ever integrate into my imaging, and this is an alternative an alternative use of the observatory rather than having it shut down because the moon's in the sky.
So I have another question for you as we sort of round out the stream. So
yes.
Uri again saying, I think to find out the mass of the planet, you also need to use the radial velocity method. Is that right?
You can apparently do it without a radial velocity measurement.
More research needed then.
I'm not in a position to tell you how. To tell you what
but it is possible to do it without.
I understand it is. Yeah.
Okay. There we go.
So yeah, for images stuck in Melbourne or stuck in locked away from their dark sky site, I thoroughly enjoyed it. I recommend you have a go at measuring the light curve of a known exoplanet. For those with observatories, why not try the TESS Object of Interest database? In this case, you actually need to measure 3 transits of an object to determine the period. It's a challenge to work out how to measure these, or how to capture data that might prove or disprove an object from this category. Do you bang away on object number 1 for a year and say, well, yep, can't find anything there, and move on? Or do you take another approach? I'm looking at on any night, moon affected night, spending half an hour on a target and moving on, and repeating those targets often rather than for a long period of time, and seeing if I can identify a transit by happening onto it. The more often I shoot it, the better chance of picking up a transit. But there is real science available here. There is real discovery to be made, particularly in that TESS Objects of Interest database.
All right, I think that brings us to the end of this morning's stream. Thank you, Tom. Wonderful presentations. Certainly piqued my interest, that's for sure. I would love the idea of getting access to some of that data and learning how to do these, run these programs. It's quite an interesting one. Thank you to everybody for joining us for this morning's stream. I hope you enjoyed the stream. Again, if you don't follow the ASV or the ASSA on Facebook and YouTube, please hit the subscribe button or the follow button. And we'll see you this afternoon at 2 p.m. for our Vic South Comet Talk, where ASV and ASSA member Michael Mattiazzo will give a presentation on the prospects of the Christmas comet C2021A1 Leonard, as well as a general discussion on comets. Until then, clear skies, and we'll see you in just under 2 hours.